Good morning, one and all. Myself, Vaidegi, working as Assistant Professor in Sri Muthukumaran Institute of Technology. Today, we are going to see the topic from the subject Analog IC Design for the 6th semester students of ECE. The topics are from the first unit of Analog IC Design. The topics are single stage amplifiers and the detailed theory presentation. Before going to the topic, let's see about the introduction to analog IC design. Analog IC design deals with circuit that processes continuous time signals such as voltage and current. These circuits form the interface between the real world and digital systems. The main focus of analog IC design is amplification, biasing, gain, bandwidth, linearity, and stability. Amplifiers are the backbone of all analog systems like sensors, communication circuits, and signal conditioning units. MOSFETs are the primary active devices used in modern analog ICs due to their scalability and low power consumption. Understanding device behavior is crucial for reliable circuit design. Single stage amplifiers are the basic building blocks of complex analog circuits. Before moving to the multi-stage amplifiers, it is essential to understand single stage operation clearly. This unit focuses on foundational concepts required for analog IC design. Mastery of this basic improves design accuracy and performance. Next we see about the basic MOS physics. MOSFET operation is based on controlling current flow using an electric field. When a voltage is applied between the gate and source, it controls the formation of a conductive channel. If the gate to source voltage exceeds the threshold voltage, an inversion layer is formed. This inversion layer allows charge carriers to move from drain to source. The drain to source voltage controls the amount of current flowing through the channel. MOSFETs operate differently depending on applied voltages. These operating conditions define different regions of operation. Understanding MOS physics helps in biasing transistors correctly. Proper biasing ensures linear amplification. This forms the basis for analog circuit analysis. Next we see about the MOSFET regions of operation. MOSFET's operation mainly in three main regions: cutoff region, triode region, and the saturation region. In the cutoff region, the gate voltage is below the threshold voltage, so no channel is formed. As a result, the drain current is nearly zero. In the triode or linear region, the gate voltage exceeds the threshold voltage and the drain voltage is small. Here, the MOSFET behaves like a voltage controlled resistor. In the saturation region, the drain voltage is sufficiently high. The drain current becomes almost independent of drain voltage. This region is ideal for amplification. Analog ICs primarily operate MOSFETs in saturation region. Correct region selection is crucial for amplifier performance. Next we see about the MOSFET small signal model. The small signal model is used to analyze MOSFET behavior for small variations around a bias point. It linearizes the nonlinear characteristics of the transistor. The transconductance GM represents how effectively the gate voltage controls the drain current. A higher transconductance results in higher gain. Output resistance R0 models the effect of channel length modulation. It affects gain and output impedance. The gate terminal is insulated, resulting in very high input impedance. This makes MOSFETs suitable for voltage amplification. Small signal models simplify circuit analysis. They are widely used in amplifier design. Understanding this model is essential for gain calculation. Next we see about the common source amplifier. The common source amplifier is the most widely used single stage amplifier. It provides high voltage with phase inversion. The input signal is applied to the gate terminal. The output is taken from the drain terminal. The source is common to both input and output. When Input voltage increases, the drain current increases. This causes a voltage drop across the drain resistor. As a result, the output voltage decreases, causing 180-degree phase shift. The voltage gain is approximately equal to minus Gm, the load resistance. CS amplifiers are used in many analog circuits. They offer good gain and moderate bandwidth. Next we see about the common source amplifier and the frequency response. The frequency response of a common source amplifier determines its performance over different frequencies. At low frequencies, coupling capacitors limit the response. These capacitors block DC but allow AC signals. At high frequencies, parasitic capacitances dominate. Gate to drain capacitance causes the Miller effect. This increases the effective point capacitance. As a result, bandwidth is reduced. The dominant pole used appears at the output node. This pole limits the high frequency gain. Proper design can improve bandwidth. The frequency analysis is essential for high speed applications. Next we see about the common gate amplifier. In the common gate amplifier, the input signal is applied to the source terminal. The gate terminal, the AC is grounded. The output is taken from the drain terminal. The configuration provides low input impedance. Due to the absence of Miller effect, it offers high bandwidth. Phase inversion does not occur in this amplifier. Common gate amplifiers are suitable for high frequency and RF amplifications. They are commonly used in current buffers. Low input impedance makes them ideal for certain signal sources, although gain is moderate, speed is high. This makes common gate amplifiers valuable in wideband circuits. Next we see about the source follower. Source follower is also known as common drain amplifier. The input is applied at the gate terminal. The output is taken from the source terminal. The voltage gain is slightly less than unity. This amplifier does not provide voltage amplification. However, it offers very high input impedance. It also provides low output impedance. This makes it suitable for impedance matching. The output voltage closely follows the input voltage. Source followers are commonly used as buffers. They prevent loading effects between stages. This configuration improves signal integrity. Next, the topic is differential amplifier and its introduction. Differential amplifiers amplify the difference between the two input signals. They reject signals that are common to both inputs. This property is known as common mode rejection. Noise and interference are often common mode signals. Hence, differential amplifiers improves noise immunity. They are very key building blocks in operational amplifiers. Differential operation enhances stability and accuracy. These amplifiers are widely used in analog ICs. Balanced signal processing is achieved using this configuration. Differential amplifiers form the input stage of most op-amps. Understanding their operation is essential for analog IC design. Next topic is differential amplifier with active load. An active load uses transistors instead of resistors. Current mirrors are commonly used as active loads. Active loads provide high output resistance. This increases voltage gain significantly. Differential signals are converted into single-ended outputs. This configuration improves the isolation between input and output. However, voltage swing is reduced. More headroom is required for proper operation. Cascade amplifiers are used in high gain applications. They are common in analog IC blocks. Designers must consider trade-offs carefully. Next we see about the cascade amplifier. The cascade amplifier combines common source and common gate stages. This combination increases output resistance. Higher output resistance leads to higher gain. Cascode configuration reduces the Miller effect. It improves the bandwidth and frequency response and also provides better isolation between the input and output. Here, the voltage swing also reduced. The cascode amplifiers are used in high gain applications and it is common for most of the analog IC blocks. Designers must consider the cascode amplifiers for the analog IC design. Next we see about the folded cascode amplifier. In the folded cascode amplifier is a modified version of the cascode. It also operates at low supply voltages. Input and output devices use different current paths. This improves voltage swing current compared to regular cascode. High gain is maintained while reducing power constraints. Folded cascodes are widely used in low voltage designs. They are popular in modern CMOS op-amps. This configuration balances gain and headroom. It also offers good frequency response. Folded cascode is ideal for low power applications. Next we see about the comparison of amplifier configurations. What we have seen in the previous slides. The comparison here follows. Different amplifier configurations serve different purposes. The common source amplifier provides high gain but moderate bandwidth. The common gate amplifier offers low input impedance and high bandwidth. Source followers provide buffering with unity gain. Cascode amplifier achieve very high gain but reduced Miller effect. Folded cascode improves voltage swing under low supply conditions. Each configuration has advantages and limitations. Selection of amplifier mainly depends on the gain, bandwidth and power requirements. Designers choose based on the application needs also. So understanding this comparison can be useful to decide which configuration will be followed in the IC design. The knowledge is crucial for analog IC engineers. Finally, we came for the summary of the lecture. In single stage amplifiers are fundamental to analog IC design. MOSFET physics directly influences amplifier behavior. Biasing determines the operating region and performance. Common source, common gate and source follower are basic configurations. Differential and cascode amplifiers enhance gain and stability. Active loads improve efficiency and performance. Each amplifier serves a specific role. Proper selection ensures reliable circuit operation. These concepts form the foundation for multi-stage amplifiers. Mastering these units is essential for the analog IC design. Hope you all understand, students. We will see in the next video. Thank you.